Hi everyone, welcome to the second of 4 videos going through some past exam questions on ligand substitution and precipitation reactions of transition metals. This question here is bringing a little bit that you need to know about that links these to sort of biological relevance. Talking about hemoglobin, as it says, hemoglobin is a complex of iron 2, so it's got this Fe2 plus complex ion in it. So it's asking us, explain how ligand substitutions allow hemoglobin to transport oxygen in the blood. Okay. So the way this works then is that the oxygen molecule acts as a ligand to the iron Fe2 plus ion in the complex that's in hemoglobin. So what we can say is in the lungs, when you're picking up oxygen, oxygen acts as a ligand. And let's show that we know what that is by donating a lone pair. I don't think we'd need to do this, but might as well revise what a ligand is. By donating a lone pair of electrons to form a coordinate bond to Fe2 plus. So the oxygen goes on as a ligand, but then we need to have a ligand substitution reaction, right? The reason this is useful is because you can get the oxygen off again, right? If oxygen just bonds to the hemoglobin and stays there, that's not any good to us, is it? We need to get to the tissues where the oxygen is needed, and then the oxygen can be released. And so it does a substitution reaction with carbon dioxide, right? So we can then say in the tissues, the O2 ligand is substituted, I can't write, by CO2. And that's it, really. I think that's all we need to put. Okay, then says, in the presence of carbon monoxide, less oxygen is transported in the blood. We know that carbon monoxide is toxic. And it says, in terms of stability constants, suggest why. Now, this bit about stability constants is not on the specification anymore, right? You don't need to know about that. But this bit about carbon monoxide is still on the specification. So you could be asked this question, but it won't talk about stability constants. Okay. So what we can say is that when carbon monoxide acts as a ligand, it forms a very strong coordinate bond to the Fe2 plus. And that's the problem, that you can do a ligand substitution, put your carbon monoxide on, when you then try and substitute it the other way and have the oxygen go on and the carbon monoxide come off, but that's not going to happen, or it's not going to happen easily. Because the bond that's formed with the carbon monoxide is so much stronger, it's almost irreversible. So that makes it very difficult. And so that is all we need to write, for our specification. This bit about stability constants, you could then just say the complex with CO as a ligand has a higher stability constant. I mean, that's all a stability constant is. It's measuring the strength, really, but you won't be asked about stability constants on your exam. So I don't need to worry about that part. But you do need to be aware of carbon monoxide forming a bond that's very strong, so it's almost irreversible. Okay, moving on. Here we've got a question about chromium. So chromium is the other one that you actually need to know about. In the previous video, we saw about copper and the ligand substitution and precipitation reactions of copper. Chromium is the other transition metal that you're actually expected to remember. So we've got this chromium hexa-aqua complex ion. If an excess of concentrated ammonia is added, the solution changes to a violet colour. We get a hexaamine chromium complex. So this must be a ligand substitution reaction, right? It's forming a solution of a different colour, right? So it's not precipitation. Precipitation would obviously make a solid. So this must be a ligand substitution. We've swapped the H2O for the NH3. and then suggest an equation for this then. Okay, well, we'll start with this complex. And we're adding ammonia to it, and we're forming hexaamine. So we are adding, or we should say we are substituting 6 ammonia ligands. Okay, we saw in the previous video that copper only substitutes 4 ammonia ligands on, and you are expected to remember that. Chromium does substitute all 6, okay, and you are expected to remember that, but it's told us in the question anyway. So it must be all 6 ammonias going on, and therefore it's going to make the complex with the 6 ammonias as the ligands. It's still going to have a charge of 3+, because the water ligands are neutral and the ammonia ligands are neutral as well. So the charge isn't going to change, and we just have the 6 waters come off. Okay, so that's hopefully a fairly straightforward equation to be able to write. Okay, moving on. We then end up with this question, which again, if you've watched the previous video, you'll see this is a very similar question, actually, to was in the previous video, although in a different format. Okay, this is a 6-mark question. It's saying describe the reactions of either aqueous copper 2 ions or aqueous cobalt 2 ions with sodium hydroxide, with ammonia, and with hydrochloric acid. Okay, now we are definitely going to do copper, right? We are not expected to do cobalt. Again, these are questions from the old specification, but I left this in because this is still relevant. This is not relevant anymore. See, we could still get this question on the new specification, but obviously it wouldn't ask us about the cobalt. And so this is very similar to a question on the previous video where it was just saying what would be the products in each of this case. Here, they just want us to do all of it rather than filling in the gaps. Okay. If we react it with sodium hydroxide, we should link observations with equations, right? So we're going to write equations for all of this. So we're going to start with our copper hexa-aqua complex. And if we're going to add sodium hydroxide to this, then this is the one where we're going to end up with the precipitate. Okay, sodium hydroxide is going to make the precipitate of copper hydroxide. So we're going to add the sodium hydroxide. We're going to end up with the product, which is going to be copper 2 hydroxide. Okay, so here we must have 2 moles of this. And we're going to end up then with the 6 waters are going to come off, and we're going to be left with the 2 sodium ions just to maintain the charge as well. It's probably a good idea, because we're making a precipitate here, let's put state symbols on. Okay, everything's aqueous here, that's being solid. That's obviously a liquid water, and these would be aqueous sodium ions. Okay, and so we can say that this is a precipitation reaction. And we can say a pale blue precipitate is formed. Okay. So you can see we've got 6 marks here for 3 reactions, so it's going to be 2 marks each. So there's 1 mark for the equation, and then 1 mark for saying we're going to get a pale blue precipitate. Okay, because that's the observation and that's the equation. Right, with the ammonia then, again, let's do the equation. We're going to have our copper hexa-aqua. Now, if you remember, again, if you watched the previous video, copper is one we do need to remember, this reaction with copper, that it does a ligand substitution reaction. Let's put this in. But it only substitutes 4 of the ligands. Okay, so we actually only react this with 4 ammonias, and you end up making NH3, 4, H2O, 2. Charge stays the same because all the ligands are neutral, and then we just need to have the other 4 H2O coming off. Okay, and we need to remember what happens to this, so we'd get a deep blue solution forms. Remember what would happen if you added ammonia drop-wise is you'd make the precipitate to start with, and then if you kept on adding ammonia, that precipitate would then redissolve and end up with this deep blue solution with the ligand substitution reaction actually happening. Okay, and then finally with the hydrochloric acid, again we've got our copper hexa-aqua complex. And if you remember what happens here is the chloride ions act as the ligands. They substitute for the water. So again, this is a ligand substitution reaction. And again, there's a little bit of consistency of copper here where, again, only 4 ligands get substituted. So we're going to have 4 HCl here. But we don't end up with 4 chlorines and 2 waters. We just get 4 chlorines going on and all 6 waters come off. Okay. So we get CuCl4, 2 minus. Notice that I don't need to put a bracket around the chlorine here because it's just one atom. Okay, I need brackets for the NH3 and the H2O, but I don't need brackets here. It's going to have a charge of 2 minus because it was 2 plus originally, and the chloride ions all have a negative charge. So it's 2 plus, but 4 minus from those. So it ends up with a 2 minus charge. And we've got rid of all 6 of the waters. Okay. And then what would we see happening? This solution would be a yellow colour. Often when you actually do this reaction, it ends up looking green because you end up with a mixture of, it's a reversible reaction here, you get an equilibrium set up, and you end up with a mixture of this yellow solution and the original blue solution, so it can end up looking green. So you'd probably get a mark for green as well. Yeah, checking the mark scheme, you would get yellowy green or greeny yellow. I'm not sure if you'd get a mark for actually green, but yellow is what I would go for. That's what it should do in theory. It's only because there's some of this left over.